the energy, the mass of a graviton, we believe, is zero, because gravity also travels at the speed of light.
So,
Yeah,
just
so,
like a
so it's
photon,
much
it
like
would
a
have to be-
photon in
have
that
to be.
particular way.
Right,
okay.
right.
And yes, if we could ever really detect a graviton, do experiments with gravitons,
Right.
scatter gravitons off of each other, then yes, we would learn an enormous amount about general relativity and quantum mechanics.
Yeah, but will it help you merge them?
well, our
Because that's a quantum
yeah,
expression of,
Absolutely.
of gravity.
That's right. In fact, the very existence of a graviton would be the first evidence that gravity is quantized.
Right.
Wow.
And so we're assuming that there is a graviton, but
man.
verifying it would be a huge step.
Who was the first to presume that?
The idea of the graviton, I don't historically know.
So,
yeah.
but Einstein was the gravitational wave. for that.
Yeah, well,
So where you have a
he was a
wave-
reluctant gravitational wave person. He was really uncertain in 1916 and 1918 about whether they were real.
Okay.
Amazing.
Yeah.
Yeah. So I'm just saying, the quantum assumption is that where you have a wave, you also have a particle,
Yeah.
and like the photon is a wave and a particle.
Yep.
Okay.
Wow.
Okay.
That's super cool, man.
That's a good question, though. Who first introduced the very idea of a graviton? I don't know the answer.
It feels kind of natural if
Yeah.
you're going
I'm
to
going to look that one up.
quantum
Yeah.
quantify.
Yeah.
everything.
All right, this is Tash Shaw. And Tosh says, Dear Dr. Tyson, Dr. Green, Lord Nice, I'm Tosh from Orange, Australia. I'm a longtime listener, so my boyfriend bought me a subscription. I've read that other dimensions could potentially be detected through gravitational and other anomalies.
Yeah.
I was wondering how we would be able to distinguish these from any effects of dark matter. So, would there be dimensional differentiations?
Yeah. In fact, a proposal that was made a while ago is that at a collider, like the Large Hadron Collider, when you slam protons together, you can calculate and measure how much energy you have before the collision. You can measure how much energy you have after the collision. Possibility is the energy went into the other dimensions.
Oh.
And so this was missing energy signature of extra dimensions that we were again hoping we would see,
Why
but
would
we've
you
not.
presume that and not as what occurred in the first neutrino experiment?
That's right. So it could be some other particle, mysterious particle carrying away.
right.
But
'Cause
there's
in the first neutrino, they did an experiment,
Yep.
and there was
an imbalance.
Yeah, there was an imbalance. There was like you start with this much energy, and they have less,
Right.
and you accounted for all the particles.
Right.
So
You're like,
what's
well,
up with
maybe
that?
there's another particle.
But what's up with that? And they said if there is a particle, it has to be neutral, and it has to be very low mass. And the guy who proposed it was Italian, so little neutral one, neutrino,
Oh,
like Bambino, little
like
baby.
bambino, neutrino.
What you got, Jack?
Let's go to Cosmic Moss. Says, hello, everyone. Love the show and every star you've had on it. You guys are great. I love the way you teach. Please keep the education up. Dr. Tyson, Dr. Green, could theoretically a frequency be matched at 2 points in space by a microparticle uninhibited by resistance, only to be met by its astrophysical counterpart?
Neil, I think you should take this one.
I don't know that I understand the question.
Kind of like matter, antimatter, but the particle is already in existence, and then it's a counterpart that impedes, I guess, the entanglement. It's kind of like,
Okay, read the first sentence again.
all right, he goes, could theoretically a frequency, all right, so that's the, I guess, his version of the string, be matched at 2 points in space by a microparticle. So that's the entanglement.
Maybe.
Uninhibited by a resistance, only to be met by its astrophysical counterpart.
The only counterpart particles are antimatter.
That's it.
Yeah,
That's
there's no other
That's what I'm
thing.
saying.
And there's not much antimatter in the universe.
Right.
In fact, well, other than the centers of stars, we probably make all the antimatter there is in the universe on Earth. Would you say?
I haven't done the calculation, but I can imagine that.
I mean, just think about that, right?
yeah.
I mean, there's plenty of antimatter made in the center of something.
Most antimatter in the universe will get annihilated, finding matter.
immediately in the centers of the sun. So,
Right.
Yeah.
the cool part was in one of the Dan Brown stories. The Catholic Church had a vial of antimatter that they carried away.
That's so funny. Dominus is spirit. Oh, he's gone. Physics jokes, people. All right.
So yeah, I'm not quite clear. If it met its the counterpart, it would annihilate, no matter what else is
Right,
going
no
on.
matter
there.
what else is going on.
Yeah.
All right,
Okay.
so here we go. Kenny Watts says this. Hey, Dr. Tyson, Dr. Green, sup, Lord Nice. Kenny from Dothan, Alabama. Is the reason why we can't reach the absolute 0 degrees in temperature because of the CMB? Is it due to the act of time using energy to move forward, creating heat? And if we were to reach absolute 0 degrees, would space-time move forward in that region?
Interesting. I was different pieces of this, Brian. So my understanding of absolute zero is that all particle motion stops, except it doesn't because you have quantum fluctuations, even at absolute
That's
zero.
the key point right there. Yeah,
Okay.
That's the real barrier.
Okay, but why isn't the cosmic microwave background a barrier?
Well, if you didn't shield yourself from 2.7 degree photons,
Yes.
they would influence. But presumably, if you're able to shield your environment,
Yeah, but the shielding would have to be temporary because the heat transfers.
yeah, sure. But an experiment takes place over a period of time. So as
Okay.
long as your time scales are
That's true.
set right.
That's how a thermos works.
Yeah,
There's
exactly.
a time with,
yeah.
with which the
So I think it's really the uncertainty principle is a true barrier against truly having particles at a definite location not moving. That would mean position and speed were both nailed down at the same time.
Which is not
and you
happening.
can't do
Right,
that.
you're not going to do that.
not happening.
Wow.
Yeah.
So the wave function would cease to exist if you were ever to get to the place where you could get the particle to stay exactly frozen, like still and definable in one point.
Okay, so what is the temperature of that state of matter?
Well, it depends on the details. I mean, you can calculate the quantum fluctuations of a field, and if you tell me how it interacts and its mass, you can calculate its quantum fluctuations, and indeed, that's how you make predictions about the Casimir effect, where you have two metal plates and there's empty space between them.
Evacuated completely.
And yet those plates can pull together because the fluctuations of the field inside are a little bit less than the fluctuations outside. And that imbalance, you can actually calculate it and you can determine how the plates come together.
That is so freaky, man.
It's all freaky.
That is so freaky. I love it.
It's all freaky.
Oh my goodness.
Brian.
And then they attract.
Yeah.
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 Brian, you freaky dude. So we should do this every week. What do you think? No, Brian, you have a life, the centennial decade of the discovery of quantum physics. So
Exactly.
we can't have too much quantum physics out there.
Yep.
And this is for the general public?
Yeah. So we're finishing it up now. In 2027, it
Okay,
should be out.
get it out in this decade.
Yeah. That's the key thing.
Okay.
Yeah.
All right. And this year, we're recording this in 2026. This is the centennial of Edwin Hubble discovering that the Milky Way is not the only galaxy in the universe.
Wow.
He discovers that Andromeda is not just a fuzzy spiral sitting within our stars.
Right.
It's a whole
It's a
other
whole nother.
island universe out there.
I love that.
That was 100
term.
years ago. So this has been a special edition because it's an extended conversation with my friend and colleague, Brian Greene, right up the street at Columbia University. And Delight, thanks for spending the afternoon in my office.
My pleasure. It was great fun.
All right. And Chuck,
Always a
Chuck,
pleasure.
your baby.
Yes.
And catching you on YouTube, were you just smart enough?
That's right. On the Star Talk YouTube channel.
Were you just smart enough for this conversation?
Today I was the dumbass. And happy to be so.
All right. Till next time, Neil deGrasse Tyson. Keep looking up. Was that other world always there, or was it created in the moment that they had the
realization of another world.
realization?
See, it all depends on what you mean by you, because if by you have the conventional notion of a single human being,
Okay.
each version of me does see a single world, carries out a single measurement.
There
It's
it
just
is.
that if you had a God's eye view,
There it is.
you would see many versions of me with many outcomes.
But it sounds like you just pulled that out of your ass.
I didn't.
This is Star Talk. Neil deGrasse Tyson, your personal astrophysicist. Got with me Chuck Nice, baby.
What's up, Neil?
All right, this is a special Cosmic Queries edition
Okay.
because half of it is not going to be Cosmic Queries.
Oh, okay.
Half of it, I'm just going to be talking to my man.
Oh, okay. For a moment, I thought you meant you were just going to talk.
Up the street